Hey everyone, let's check out this problem. This is a limits at infinity problem. So what we see is that we're looking at limits where x goes to infinity. And if this limit does exist, say it's like the number 2, that means that there's a horizontal asymptote, y equals 2. But let's just do this limit and not talk too much about horizontal asymptotes. So here's the trick to this problem, and I think that's why I really wanted to do this video, is we have this property of logs that I'm going to use here. And what is, well, let's just go through a few of them. Log could be common log. We're going to talk about the natural log. If I have a times b, but it could be any base, 2, 10, whatever. ln a times b is ln a plus ln b. That's first property. The second one, we're not going to use that here actually, is that ln of a divided by b is equal to ln a divided by ln b. That's the one we're going to use here. So see on this one here, we have two logarithms with a subtraction, so it's a difference of logarithms. And right off, if we choose, and I do, and I'll explain why later, I can write this then as a fraction or a quotient of these two pieces. 1 plus x squared, 1 plus x. Alrighty, so that's the second property I used. Just to be complete here, let me put a third property here, which we're not using either. But if you have logarithm a to some power like t, this is equal to t ln a. I was thinking, well, what letter should I use here? Maybe x, but I use t. But that t, whatever you put up there, that's a number you can, anyway, it comes out to the front. I drew that little line like it's traveling or something, like it's alive, but anyway, I just put it over there. But that's a property. And so just, those ones you have to memorize. Okay, now, why would I do that anyway? Well, it has to do with us understanding the logarithm. And what we can do is, for now, we can just focus on the graph of logarithm. And you just either know this, believe me, and we can spend about 10 minutes explaining this part. But here's the graph, roughly speaking, of y equals ln x. And part of what we are working with, or going to accept, although we could prove it, definitely we could prove it, but that's another video, is that the limit of ln x as x goes to infinity is equal to infinity. So see, this guy grows, but it grows very slowly. And it almost looks like a horizontal asymptote. It doesn't. But I'm telling you what I mean by infinity is I can make this guy big over here. Well, just to throw you off maybe. How big do you want it to be? You want 100? If I put inside x equals e to the 100, I'll get 100. So see, if I want to get 100 here, I put e to the 100. How do I know that? Because of the property that I didn't list, is that ln and e to the x is equal to x. Okay, so now I'm getting off on logarithms. Let's not go too far on that, but believe me, this graph grows slowly. And so the result is that this limit here is infinity. When you put larger and larger numbers, logarithm does get big. So on this guy, ln is the input, 1 plus x squared, gets larger and larger, goes to infinity. This goes to infinity. Then over here, the inside, 1 plus x goes to infinity. That goes to infinity. Now someone might say, well, I'm just going to subtract infinity minus infinity. It doesn't work that way, because this first one might be, for any value of x, this first expression might be way bigger than the second expression. Or they might be pretty close to each other. Or the second expression might be really bigger. And when I say infinity, it's not a number. What it means is that these functions get very large. But say one might be a trillion, that's huge. The other one might be a billion, also huge. But a trillion minus a billion is not zero. I mean, so we can't, we don't subtract infinity. But what we can do is do a fraction here. And then I'll just put like a little squiggle for a moment. I'll find the limit of what's inside. I'll work on this. At this point, if you wanted, you could use L'Hopital's rule, but we haven't done that yet. We're doing that in the next chapter. So what I do here is I have 1 plus x squared or 1 plus x. What I'm going to do is this is a rational function. I divide by the highest degree term in the denominator, which is x. I'll do that to the top and the bottom, to the numerator and denominator. So therefore, when I multiply that through, I get 1 over x, 1 over x times 1. That's 1 over x. 1 over x, 1 over x times x squared, that's x. Divide by 1 over x times 1, that's 1 over x. 1 over x times x, that's 1. So what I see is the denominator that gives 0 plus 1. The numerator, I get 1 over x goes to 0. X goes to infinity. The numerator is getting very large. The denominator is approaching 1 because I have 0 plus 1. The numerator gets large. This whole thing is infinity. So what the result is this inside piece here is getting larger. It's going to infinity. So in fact, if you want to write this step, I don't think you need to write it, but you could say that, coming back with this, okay, this is like an aside. It's like a little thought bubble. But coming back now with this right here, continuing on this, continuing on that thought, let's write equals now. Continuing this equals limit. If you want to write this, you can write ln and call this whole thing u, and u goes to infinity. You could do that, or I just sort of like drawing the arrow. This inside part goes to infinity. That means the inside gets bigger. We already said as the input of logarithm gets bigger and bigger, our limit's infinity. As the input approaches infinity, we get infinity. So on this, I'm going to write infinity, and that's our answer. But you didn't have to really write that line that I just wrote there, I don't think. You could just put it right here as infinity. But we had to make a proof that the input is infinity. It's using continuity of logarithm that you can do that. But the inside is going to infinity. So, yeah. Actually, now I think of it, maybe it didn't even use continuity, but that's, okay, but anyway, the inside part here goes to infinity, so logarithm that goes to infinity. So just as long as we have this limit ln goes to infinity. Okay, let's just put a little box around this. And, oh man, math is sort of challenging, but it's like so many other things. The more you put in, the more you get out. So it's pretty fun. I just feel like if you majored in math, I don't know, there's a lot of things you can do with that. A lot of applications. Okay, everybody stay safe. Let's live in a safe world. Wouldn't that be awesome? No war. Everybody's safe, healthy. Okay, take care, everybody. Bye.